Okay, so now a new definition. Let the set X together with the relation less than or equal to be a poset, and let the set S be a non-empty subset of the set X if there exists an element U in the underlying set X such that for every element S in the set S, we have that the element S is less than or equal to this element U. Then this element U is an upper bound for the set S. And we say that the set S is bounded above. And on the other extreme, if there exists an element L in the underlying set X, such that for every element S in the set S, this element L is less than or equal to the elements S in the set S, then this element L is a lower bound for the set S. And we say that S is bounded below. The set S is bounded if it is both bounded above and bounded below. So notice in particular that the upper bound and the lower bound for a given set S need not be in the set S itself, but it must be in the set for which S is a subset, where that set has the with the relation less than or equal to is a poset. Now there are two special bounds, the least upper bound and the greatest lower bound. So this is a new definition. If the set S is bounded above, then the least upper bound for the set S is called its supremum. And is denoted sup S. And if the set S is bounded below, then the greatest lower bound of the set S is called its infimum. And is denoted inf S. So notice that if the supremum of the set S is itself an element in the set S, then the supremum of the set S is the largest element in the set S. And if the infimum of the set S is itself an element in the set S, then the infimum of the set S is the smallest element in the set S. Okay? So now I need to remind you of a theorem that we gave back when we first started looking at a basis for a topology. So recall the following theorem. Let X together with some topology tau be a topological space. And let the collection script B be a basis for the topology tau. Then a given set U is open, or in the topology, if and only if, for every element X in the set U, there exists an element in the basis such that that element X is in this basis element, which is itself a subset of the set U. So again, a set is open if and only if for every element in that set there exists a basis element containing it, which is a subset of the given set U. All right? So now we're ready for a big theorem. Big in the sense that it takes a little bit of work to prove it. So let the collection X sub I, delta, or D sub I, for I a positive integer, be a countable collection of metric spaces and let rho sub I, taking as an argument X sub I and Y sub I, which is the smaller of the two values, being either the distance under the metric D sub I from X sub I to Y sub I, or 1. Let this rho be the standard bounded metric. Corresponding to the metric D sub I, and this is for every metric space, X sub I. Then define a function D mapping the product, the countable product of these spaces, into non-negative real numbers by D of X, Y is the supremum of the set consisting of the countable sequence formed by rho sub I of X sub I, Y sub I, over I, where these points, X using vector notation is the point consisting of coordinates X sub I for I in the set of positive integers, and Y in vector notation, again being the point consisting of coordinates Y sub I, where I is a positive integer, are points in the product space and the countable product space. And with this function, this metric, this D, capital D, is a metric that induces the product topology. On the countable product. Okay, so this is a long theorem, so let's go over it again. Given a countable collection of metric spaces, we take the standard bounded metric for each metric on the space, and use this to define a new function, capital delta, from the product, the countable product of spaces x of I into non-negative real numbers, and we take the value of this function is the supremum of all the ratios of rho sub I, being the distance from x sub I to y sub I over I, for any 2 points in the product space. Then this metric D is in fact a metric that induces the product topology on the product space. Okay, so now we need to prove it. We first need to show that this function D is a metric. Now, non-degeneracy and symmetry are trivial. So we will show that this function D satisfies the triangle inequality Now, as each function rho sub I is the standard bounded metric for the underlying space x of I, as each rho sub I is a metric for every index I, we have for every index I in the set of positive integers that rho sub I of x sub I, y sub I is less than or equal to rho sub I of x sub I, z sub I plus rho sub I from z sub I to y sub I. So, for every index I, we have that the if we divide each term by the integer I, that rho sub I from x sub I to y sub I divided by I is less than or equal to rho sub I from x sub I to z sub I divided by I plus rho sub I from z sub I to y sub I divided by I. Now, by the definition of the metric capital D, we know that rho sub I from any point u sub I to v sub I over I is less than or equal to its supremum. This is part of a set being constructed as a sequence of ratios, and so each given ratio of rho sub I to I is less than or equal to the supremum in that set, which is the metric capital D, or the function capital D. So we can replace these two terms with the metric D. And so for every index I, we have that rho sub I from x sub I to y sub I over I is less than or equal to the value of the function d from x to z plus the value of the function d from z to y. So notice that this statement says that for every index I, the ratio of rho sub I to I is bounded above by the sum of the values of the function d, taking as an argument the pair xz and then the pair zy. So the supremum of the ratio of rho, taking as an argument x sub I to y sub I, to I, is less than or equal to this sum, as the supremum is the least upper bound. This is an upper bound, so the least upper bound must be smaller than or equal to this value. And so, in other words, d of xy is less than or equal to d of xz plus d of zy. So the triangle inequality holds. And therefore the function d is a metric on the countable product of spaces x sub I. All right? So we next need to show that every open set in the metric topology on the product space, the countable product space, this being the metric topology induced by the metric big D, is open in the product topology. And the converse, that every set open in the product topology is also open in the metric topology.